Hello and welcome to lecture number 9. So we will talk about scattering of lights by colloids. This is one of the most important and striking characteristic features of colloidal suspension. Suppose we have a colloidal dispersion and the dispersion medium could be air or could be liquid, water, etc. And if we shine visible light to the colloidal dispersion. Now, a portion of this visible light may be absorbed by the colloidal dispersion and a portion of light may go as it is without disturbed. So we call it the transmitted light. So a portion gets transmitted and the third portion it undergoes scattering. So there is a significant amount of scattered light when visible light is incident upon a colloidal dispersion. So we will talk a little bit about this scattering of colloids. Very basic, very elementary stuffs. So firstly, let me tell you, this scattering of light, this is not reflection. Okay, so that means sometime you may see that some dust particles when like a ray of sun comes to hit him, especially in the morning time. You can see these dust particles floating in the air and they're shining. So that's not scattering though. This is basically a reflection of light by the suspended dust particle. Because scattering of light, because a particle scattering light cannot be uh, mm, uh, seen by naked eye. Okay, so definitely this is not a reflection. So this is a physical phenomenon. So there is some physics behind it. So let me try to define the scattering in as simple way as possible. So suppose an electromagnetic radiation hits an atom. Okay, so remember it's an atomic phenomenon, and in atom we have electron clouds. Now this electromagnetic radiation has a particular frequency nu. So whenever the electromagnetic radiation hits the atom has the electron cloud. So we can write that electron cloud also starts to oscillate periodically. Okay. So in a periodic manner, the electron cloud starts to oscillate. And whenever there is a periodically oscillating electron cloud, so that oscillating electron cloud would be a source of a fresh new electromagnetic radiation. So that periodic oscillation would give rise to another radiation, or that means it may serve as a source of radiation. Okay, and therefore it would give off H nu prime. So another electromagnetic radiation. So now if the nu prime, that means the newly generated frequency is equal to nu, we call that the scattering is elastic. So this happens during elastic scattering. So the entire process is basically the scattering. That means there will be a periodic oscillation of electron cloud due to an incident electromagnetic radiation, and the atom itself would behave as a, as an oscillator, or it would behave or serve as a source of a new radiation. And if nu prime is not equal to nu, then we call this is an inelastic scattering. Okay. So therefore, we can proceed with few examples so that it will be clear to us that an example of elastic scattering is Raleigh scattering. Probably you have heard the name of such kind of scattering. And an example of inelastic scattering is Raman scattering. So the basic idea of the Raleigh scattering is the colloidal particles when undergo Raleigh scattering, it would not change the incident frequency of the light. So, but in Raman scattering, it changes. And we understand that Raman scattering is a molecular phenomenon, and many molecules demonstrate Raman scattering, they show Raman scattering. So anyway, uh, in colloidal particle, mostly the most prevalent, the most common type of scattering is the elastic scattering of Raleigh type. Alright, so now we will briefly talk about a few details of the Raleigh scattering, and there are a few basic types of Raleigh scattering. So for example, a Tyndall effect that I already talked about is a type of Raleigh scattering, and in what kind of condition we get Tyndall scattering and any other type of scattering, those come under Raleigh. So we'll talk about now. So now we talk a little bit about Raleigh scattering. In Raleigh scattering, you see the scattering particles are small and small enough to act as a point source of light. So what are the size range for particles to show Raleigh scattering? So basically they are from molecular size to somewhat around 40 nanometer approximately. So as an example, we can think about the molecular oxygen. The molecular oxygen scatters the light, and the scattering is according to the Raleigh type of scattering. And another striking feature of the Raleigh scattering is the intensity of the scattered light is actually inversely proportional to lambda to the power 4, where lambda is the wavelength of the light that are getting scattered. So now you can obviously, in the visible region, we have the blue lights have the smaller lambda and red lights have larger lambda. So therefore, the probability of the blue light of getting scattered is much higher. So therefore, what happens that whenever molecular oxygen scatters light, it can effectively scatter the blue light in much more extent than in other wavelengths in the white light coming from the sun. So therefore, as I told you, that whenever lights get scattered, the intensity is maximum at the 90-degree angle. So in atmosphere, when white light passes through, the maximum amount of blue light that gets scattered in the atmosphere, in the outer atmosphere, and it comes down towards the earth. So maximum blue light coming through makes the sky appear to blue. All right. But in Raleigh scattering, there are two special types, special cases. So one is called obviously the Tyndall scattering. So that we have already discussed a little bit before. And there is another type of scattering, it's called the Mie scattering. Okay. So I will come back to the Tyndall scattering once again a little bit, but there is a new type of scattering term we are referring to. So let's try to understand in a very basic sense that what type of scattering is known as Mie scattering. So in other words, the Mie scattering to happen, there are certain preconditions to be fulfilled. So let's clean the board and explain to you what are those conditions. So Mie scattering is a special type of Raleigh scattering. It happens only when these three conditions are fulfilled. So these are: number one, there is a significant difference of refractive index between the particle and the suspension medium. Number 2, when the particle size range uh, is within the visible wavelength of light. And thirdly, that is most important, when the particles are essentially spherical in shape. Okay. So whenever these three conditions are fulfilled, we get a special type of scattering called ring scattering, and usually it is observed for particle size between 300 nanometer to 600 nanometer. So in this region, gold solve, sulfur solve, I mean these are the colloidal particles taken in water suspension medium, etc. Even clouds, okay. So the white appearance, the white nature of clouds, it's also due to the ring scattering. And sometimes there is a nice white glow visible around the sun. It is also due to ring scattering. Okay, so now the question is, there is some difference between Rayleigh scattering and Mie scattering. Okay, so next I will try to illustrate both the two types of scattering, Rayleigh and Mie, and we'll try to tell you what are those two basic differences between Rayleigh and Mie scattering. Although Mie scattering is a type of Rayleigh scattering, but there are some differences. So the major similarity between the two is both are elastic scattering. Okay, so let me try to explain the difference. So the difference between Rayleigh scattering and Mie scattering can be presented in this manner. So I have drawn two arrow heads in two opposite directions. So in scattering, these lobes, so we can call these as a scattered lobe. So these lobes are known as, one of these as back scattered lobe and another is the forward scattered lobe. Now in Rayleigh scattering, both the intensities of the back scattered and forward scattered lights are almost equal. But in Mie scattering, the intensity of the forward scattered lobe is much more than the back scattered lobe. So that is the major difference between the two, and it happens because like I said, that there is certain size range of the particles and particles have to be spherical. So spherical particles between 300 to 600 nanometers having a varying refractive index compared to the dispersion medium show such kind of special type of behavior. Another important thing is Rayleigh scattering is highly dependent on lambda that we have seen. So that means from white light it will only successfully scatter the blue light more and least scattering for red light. So therefore obviously the scattering efficiency is relatively less if we compare about, if we consider the total scattering with respect to the incident white light, the scattering efficiency is less because it is selective on lambda. But as opposed to Mie scattering, it is not so dependent on lambda. So therefore you can imagine that whatever the white light is coming, the spherical particles can successfully scatter those light. So with a heavy amount of forward scattering, and all the wavelengths of white light would be almost equally scattered in the forward direction. So therefore, the intensity, if we compare it with respect to the incident white light, the intensity of scattered light for Mie scattering appear to be more than that of the Rayleigh scattering. But remember, I am comparing about the different wavelengths that are present in the white light. Okay, so therefore we can take two classical examples. That is, the blue sky is the example of Rayleigh scattering, but the white cloud, the appearance of the white nature of the cloud or the white glare around the sun appearing due to Mie scattering. And the white nature of the milk, the colloidal suspension of some emulsion particles in milk, uh, that is somewhat believed to be due to Mie scattering of white light. Anyway, so these are the major difference between the two types of scattering. Now we talk a little bit about the Tyndall scattering that we have already done. So we have to just learn one more application about the Tyndall scattering. So let's delete this part and talk about it. As I mentioned before, that Tyndall scattering is actually a type of Raleigh scattering, but it occurs with particles from 40 nanometer to 900 nanometer, so much larger than the Raleigh scattered particles. But once again here, the underlying condition is that the refractive index of the particles much differ to a significant extent compared to its dispersion medium. Now, through the Tyndall scattering, it has been possible to measure a variety of colloidal salts and aerosols. Okay. And its major applications, as also it has been discussed, that it is applied in ultramicroscopy to measure turbidity in air, in other words, the air pollution. And also another thing that's called dynamic light scattering. Now, this dynamic light scattering is a technique that nowadays are always coupled with particle electrophoresis. So, using particle electrophoresis, we measure the zeta potential, and while we measure the zeta potential, the movement of the particle is tracked. Earlier, it used to be tracked by simple ultramicroscope developed by Zygmonti, but nowadays it is tracked by, again, Tyndall scattering, but it is somewhat coupled with a technique. It is called the dynamic light scattering. So what's that? I will try to explain you in as simple manner as possible. So imagine there is a particle, it is a colloidal sol, and this colloidal sol is excited with a monochromatic laser source. Okay, monochromatic laser H. And then what happens is definitely this particle scatters the monochromatic light source. So once this scattering is successful, it would create a scattered intensity, all right, and that intensity is captured. But remember, these particles are somewhat in motion. Okay, so that means if we do not apply the electric field, so these particles are subjected to the random thermal motion or Brownian motion. So due to this random Brownian motion, it's made possible that these particles may move towards the observer or may move away from the observer. So if it moves towards the observer, according to the Doppler effect, we actually observe a laser Doppler effect. So the laser Doppler effect says that if the particle moves towards the observer, so the intensity of the scattered light increases. Okay, and if the particle moves away from the observer, the frequency of the scattered light gets decreased. So in other words, particle moves towards the observer, the frequency of the scattered light gets increased, and the opposite direction, if it moves, the frequency gets decreased. So what happens that there is a broadening of frequency due to the Doppler effect is observed. Now, this broadening of frequency, all right, so this can be referred as delta. So this broadening is dependent on the particle diameter. Remember the Einstein's equation? So using some basic equations of diffusion and this scattering and this, Doppler effect, etc. There is a relationship between this broadening of Doppler frequency with the size or the diameter of the particles, and by measuring this broadening, it is possible to figure out uh, the respective diameters of the particle, and oftentimes we observe a distribution of the particle size. So a dispersion curve, the mini histogram, we see a different size distribution plots. All right, so that's how the dynamic light scattering data tells us. So we get a size distribution data. So from the size distribution data, of course, we can measure the mean diameter and etc. So in the commercially available uh, electrophoretic equipment that is equipped to measure the zeta potential is also comes with the dynamic light scattering facility, and this dynamic light scattering technique is actually a measure of the diameter of the particles uh, that is based on the laser Doppler effect, or the broadening of the frequency of scattered light due to Doppler effect of the laser source. So in these colloidal science, these instruments that measures the zeta potential and also that analyzes the DLS, dynamic light scattering, these are very important techniques, and people researching on this topic, that means nanoscience, material science, colloids and surface science, they oftentimes analyze these data, they perform these experiments, and they have to discuss and represent the data for publication of a research work. So I hope through these lectures, especially today's lecture, you have some basic idea that how you know sizes of the colloidal particles are analyzed or characterized through microscopy and then scattering. Okay, so with this we finish our lecture today, and from the next lecture we will move on to our third chapter, and we will come across some fresh new topics. So we'll see you then in the next lecture. Till then, goodbye.